This is official podcast of Global Eco Trading, an international trading and business consulting company. We conduct trading operations and providing access to exclusive brands and products. Our experience and expertise helps to get high-quality products and reduce our clients' operations costs. We supply not only merchandise, but trust and value. Welcome back to the Deep Dive. Today, we are jumping right into a subject that really sits at the intersection of material science and, real-world industrial maintenance.
It really does.
We're talking about operational excellence, specifically when it comes to rolling bearings.
A critical component.
Absolutely. We've been looking at a stack of sources detailing best practices for machinery longevity, and there's this one really alarming theme that keeps coming up, a maintenance failure that is completely avoidable.
Shockingly common, though.
Shockingly common. We're talking about components engineered for decades of service being, destroyed in just a few seconds. Okay, let's unpack this.
Let's do it.
Our mission today is to understand why a simple, inexpensive tool, the hammer, is probably the single greatest threat to the life of these critical components. And how, ignoring that threat just immediately negates the value of any high-end part you've just bought.
That's the core vulnerability, isn't it?
Yeah.
When we talk about supplying trust and value, as we do, that value has to be maintained through the entire process, not just the component quality, but the installation quality.
Right.
A rolling bearing it's a masterpiece of precision engineering. It's designed for immense loads, micron-level tolerances, but then a momentary lapse during mounting. Someone grabs the hammer for a quick fix.
And it's all gone.
It is a guarantee of premature, catastrophic failure. You might have a multi-million-dollar piece of machinery, but its operation relies entirely on the integrity of a component that might cost a few $100s. You just have to respect the engineering.
Okay, so let's start at the most basic level. The design failure. What are rolling bearings actually designed to handle, and why does an impact force, a hammer blow, just immediately violate that principle?
Well, fundamentally, rolling bearings are optimized for distributed rotational loads.
Okay, distributed.
Exactly. Think of a heavy shaft spinning. The weight, the pressure, it's all constantly spread out across all the rolling elements, the balls or the rollers.
So it's shared.
It's shared. The whole design is built to manage friction and spread that stress evenly. This ensures what we call elastic deformation. The steel flexes a tiny bit, and then it returns to its original shape.
Elastic deformation. So it bends, but it doesn't break.
Precisely. That's how you get 50,000 operational hours. Now, introduce a hammer. When a tech strikes a bearing ring, even with what seems like a moderate blow, they are injecting a massive, sharp impulse force.
So it's not distributed anymore.
It's the complete opposite. It's a point contact. At that exact point of impact, the stress concentration just skyrockets, and it far exceeds the material's yield limits. You've gone from elastic deformation into plastic deformation.
Meaning it's permanent.
It's permanently scarred. The metal is changed forever. The result isn't just, a little mark. It's a fundamental engineering violation.
So when that shockwave hits, the damage is already done. It doesn't matter if the bearing is spinning or not. It's no longer a precision component.
It's compromised.
Okay, so let's get into the specifics then. The sources show 4 distinct ways this impulse just destroys the bearing. What's the first one?
The first is the most direct result of that force. Point load over stress.
Right.
Bearings are rated for huge loads, dynamic and static loads measured in tons. But those tons have to be applied across the entire circumference. When you apply that force to a single tiny point,
The material just can't take it.
it's an instantaneous failure. You get immediate structural consequences. We're talking about micro cracks forming internally that you can't even see, permanent indentations on the raceways, even slight deformations of the ring itself. That bearing now has a built-in failure point before the machine is even turned on.
And that damage, it immediately leads to the second path, which is brinelling. Now, we hear this term, but specifically, we're talking about true brinelling here.
That's a key distinction.
True brinelling is from a static overload impact. The rolling elements, the little balls or rollers, they basically act like tiny anvils. When that hammer force drives through them, they press permanent dimples into the raceways.
You've taken a surface that's measured for smoothness in millionths of an inch.
And you've just pitted it.
You've pitted it with sharp-edged indentations. And just for context, there's also something called false brinelling, which is different. That's usually from vibration when the machine isn't running.
Right, that's more like fretting corrosion.
Exactly. The hammer blow, this is true brinelling. It's a physical, permanent deformation. So when that bearing finally rotates, those dimples create massive, repetitive stresses every single time a ball rolls over them.
And that leads directly to vibration.
Massive vibration, noise, overheating.
Yeah.
It dramatically accelerates every other failure mode.
Okay, so moving on. The third destructive path is internal misalignment. This one feels a little more subtle, but just as destructive.
It's incredibly destructive. When you strike only one ring, say, you're hammering the outer ring into a housing. You're forcing that massive installation force to go through the rolling elements to the other ring.
But they're not designed for that.
Not at all. The rolling elements and the cage that holds them, they're designed to maintain separation during rotation, not transmit installation force.
So the force transfer is uneven.
It's violent and uneven. It can permanently skew the inner ring relative to the outer ring. And even worse, the cages, which are often made of polymer or softer metals, they're fragile. That shockwave can literally fracture the cage.
And if the cage is damaged?
The balls clump together. Friction increases exponentially. Catastrophic seizure is right around the corner.
Which brings us to the fourth path, the material science of it all. Surface hardness breakdown.
Right, and this gets to the heart of the precision engineering.
Bearing raceways and balls aren't just simple steel. They're intensely heat-treated, right? They can exceed 60 on the Rockwell hardness scale, 60 HRC.
That's incredibly hard.
For our listeners, that's almost as hard as a ceramic or carbide tip. And that hardness is necessary to resist all the stress and fatigue over years of use.
But that high hardness comes at a cost. It makes the surface extremely durable against normal rolling wear, but it achieves that by sacrificing ductility.
It becomes brittle.
Intentionally brittle. So when a hammer delivers that sharp impulse, it introduces plastic deformation below the surface layer, physically breaking the engineered crystalline structure.
You've shattered the protective layer.
You've shattered it from underneath. That failure immediately creates subsurface fatigue. So when the bearing finally runs, that microscopic damage quickly turns into visible cracks.
And that sets the stage for early spalling.
Exactly. Spalling, which is the flaking or peeling of the surface material. So instead of lasting 50,000 hours, you see the surface start to fail within just hundreds of hours, all because its foundational integrity was compromised right at installation.
It's clear the damage is just. It's inevitable. But let's quantify this for, the operational manager or the business owner. What is the real cost of this seemingly small shortcut?
The real cost is never the bearing itself. It's the unexpected, unscheduled downtime.
The shutdown.
The shutdown. And the sources are absolutely brutal on this. We are talking about reducing the intended operational life by an unbelievable margin. The expectation might be, 50,000 hours?
Which is years of continuous service?
Years. But an improperly mounted bearing, damaged by even one single sharp blow, can see that life reduced to 500 hours.
500. That's wiping out 99% of its lifespan.
It's gone. 500 hours is less than a month of continuous runtime. So you take a high-quality component, something supplied with trust and value, you install it improperly, and it goes from a multi-year asset to a multi-week ticking time bomb.
And is that really from just one hit? Or is that from repeated bad practice?
The data shows that a single improper blow to the wrong surface can initiate enough damage to cause that drastic failure. The machine doesn't just stop. It fails suddenly, catastrophically. And it often damages other components on the way out.
So the cost to replace the bearing is nothing?
It's irrelevant. It's irrelevant compared to the hundreds of thousands of dollars per hour of lost production. I read one failure analysis. A $75 bearing, improperly hammered onto a shaft, failed in under 2 weeks.
Wow.
It shut down a $4 million conveyor system for 3 days. The cause was traced back purely to the installation technique. I mean, the cost-benefit analysis is a joke. You save 2 minutes with a hammer versus 3 days of lost production.
That really grounds it. The risk is immense. We have to stop seeing the hammer as a tool in this context and start seeing it as an instrument of destruction.
For precision machinery, absolutely.
So if the hammer is the villain, how do maintenance teams do it right? How do they uphold that trust and value? The source material is very clear on this.
It is. You have to respect the physics and the material science. The mounting process must use either controlled thermal expansion or uniformly distributed mechanical force. Never point impact.
Okay, so let's start with thermal.
The gold standard for mounting an inner ring onto a shaft is thermal expansion. This involves using a specialized induction bearing heater.
How does that work?
It creates a magnetic field that rapidly and evenly heats the bearing ring. Metal expands when heated, so the inner diameter grows just slightly. You heat it to around 100, maybe 120 degrees Celsius, and you get just enough clearance.
And that's better because the expansion is uniform.
Perfectly uniform. The bearing slides smoothly onto the shaft without any mechanical force whatsoever.
If there's no shock.
Zero shock, zero brinelling, zero misalignment. The thermal method ensures the internal integrity is perfectly maintained. It's clean, controlled, and repeatable.
Okay, that provides incredible value. But what if thermal isn't an option? Or for fitting the outer ring into a housing?
Then you turn to professional even force application. This means using a dedicated professional bearing mounting tool set.
So, specific tools for the job.
Specific tools. These kits have precision impact rings and sleeves sized for the exact bearing you're installing. And the key is where the force is applied.
Right.
If you're fitting the inner ring onto a shaft, the sleeve contacts only the inner ring. The force never has to travel through the delicate rolling elements.
And same for the outer ring and housing, I assume.
Exactly. The sleeve contacts only the outer ring. This completely eliminates that destructive force transmission through the cage and balls. It prevents all the damage we've been talking about.
So the principle is simple. Force must only be applied to the ring that's actually moving, and it has to be uniform, no localized pressure.
Precisely. We're dealing with components where tolerances are measured in microns. Trying to install a micron-precise component with a shock tool designed for demolition. It's just a recipe for disaster. Using the right tool is the difference between respecting the design and guaranteeing its failure.
So, what does this all mean? The core takeaway for you, the listener, is simple. Never hammer bearings into place. The cost savings of that shortcut are immediately canceled out by the guaranteed internal defects. High-quality components require high-quality installation to deliver the life you expect.
And this raises a really important question for you to consider about your broader maintenance culture. The seamless operation of a massive, critical machine often depends on the proper installation of its smallest, most delicate parts. If your organization is having unscheduled breakdowns, how often are those failures traced back, not to the component, but to a seemingly minor installation shortcut?
That's a powerful thought.
Look at your preventative maintenance checklist. Make sure the hammer is listed as a prohibited item for bearing installation. The quality of your processes directly dictates the life of your expensive assets.
A compelling and essential message. The smallest details really do create the biggest difference in operational efficiency and, ultimately, the bottom line.
All right.
Thank you for joining us. This was the Global Ichio Trading Podcast. Subscribe so you don't miss upcoming episodes covering the latest business news. See you in the next episode.